In the last lecture, we saw how to calculate how much work is done due to gravity. Now, I should mention though, it's not necessary for objects to fall exactly downwards. Take this bowling ball for example. It weighs 2.5 kg and we set up a ramp so that this bowling ball goes from 4 meters height to 0.5 meters height. Now, if I ask you how much work was done, how would you answer that? Let's do it exactly the same way as we did in the last lecture. At 4 meters height, the bowling ball should have a potential energy of 2.5 times 9.8 times 4, which equals 98 joules, and at the end point it should have 2.5 times 9.8 times 0.5, which equals 12.25 joules of potential energy. That means when the ball rolls down, 85.75 joules of energy was converted into other forms of energy, or simply 85.75 joules of work was done. In fact, it doesn't even have to be a straight ramp. Whatever the shape may be, if the starting and ending height is fixed, it would always yield the same amount of work. And if we assume that all of this work was converted into kinetic energy, we could predict how much speed the bowling ball should have at the end of the ramp. But I digress. However, if we wanted, we could make this calculation a bit easier if we wanted. Let's define something called gravitational potential V, which is just the product of g and h, gravitational acceleration and height. That gives us our new equation U equals mv. Note that here V is gravitational potential and U is gravitational potential energy. They are not the same. In fact, the relation between them is given by this very equation U equals mv. Remember, since potential energy U is dependent on what you take as reference height, gravitational potential V also depends on reference. From gravitational potential's definition V equals gh, G is a constant, so we can specify a potential for every single height. For example, at 4 meters height, the potential would be 9.8 meters per second squared times 4 meters, which equals 39.2 units. Similarly, at 3 meters height, the potential would be 29.4 units, at 2 meters 19.6 units, at 1 meter 9.8 units, and at 0 meters potential would be 0 units. By the way, like before, the potential at the reference height will be 0 units since the height h is 0 meters. And like before, any height below 0 meters will be negative and have a negative potential. This gives us a new way to look at the problem. Let's say you have Shinigami eyes that can see numbers floating at every point telling you the potential at that point. Then how would you calculate the amount of work done? Well, all you have to do is multiply the mass of the object to get the potential energy at the starting and ending point, and energy difference will tell you how much work was done. Let's take a look at that bowling ball example to clear everything up. At 4 meters height, the potential was 39.2 units. So if the ball was 2.5 kg at that height, it would have a gravitational potential energy of 2.5 times 39.2, which equals 98 joules. At 0.5 meters height, it would have a potential of 9.8 times 0.5, which equals 4.9 units. And since the bowling ball has a mass of 2.5 kg, the potential energy U would be 12.25 joules. And just like before, the energy difference would be the amount of work done. You might think introducing a new quantity like gravitational potential V, was that really necessary? Because before, all we had to do was just multiply m, g, and h. And now we're first multiplying g and h, which we are calling potential V, and then multiplying V with mass m to get energy U. We're just doing the same thing, so was that really worth it? Actually, you would be exactly correct in this case. As long as this U equals mgh formula applies, you don't have to worry about the potentials. But this formula doesn't always work, because it doesn't account for the Earth's curvature, and for this formula to work, g needs to be a constant. So this formula is useless if you are trying to keep your satellite in orbit. If you tried to consider these facts, the formula would quickly get out of hand. But fortunately, U equals mv still applies. Just bundle everything into that gravitational potential V and it's just as simple as before. All you need to know is the value of V. That's where those Shinigami eyes will come in very handy. That or the value of potential will be provided in the question. Take a look at this Mario jump, for example, to see how we will use the potential. Mario is standing on a platform which has 39.2 unit of potential and jumps to somewhere that has negative 4.9 units of potential. Given Mario weighs 89 kg, his potential energy at the starting point will be 89 times 39.2 joules, and at the lower end it would be 89 times negative 4.9 joules, which just equals 3488.8 joules and negative 436.1 joules respectively. And by jumping, Mario would have done 3924.9 joules of work. If you are trying to calculate the amount of work done, you could get even fancier and skip one or two lines like this. Now, you could directly use the gravitational potential difference del V to calculate the work done like this. If you try a few examples on your own, you will get the hang of it. Let's do exactly that in the problems section.